the force in the x direction equals the negative derivative of the potential energy associated with that force with respect to position. This is true for something called conservative forces. Before we make sure you understand what conservative forces means, we are going to say, this is not, again, not on your equation sheet. It's something you need to have memorized. Yes?
Is that derivative of U?
Derivative of U, yes, the potential energy. So U stands for the potential energy associated with that force. I'm going to go through some examples so you get some idea of what that means. So it's the force in the x direction is equal to the negative of the derivative of the potential energy associated with the force with respect to position. A conservative force is simply a force where the overall, only the start and finish locations matter when you have a force change something from one location to another. In other words, friction is a non-conservative force because the path matters for friction. For a conservative force, it is independent of the path. And a lot of the forces that you deal with in this class, like the force of gravity, the force of spring, etc., are all conservative forces. Friction is the one non-conservative force that you are going to deal with. So, if the question says we have a conservative force and the equation is blah, 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 it should pop in your brain, ah yes, I know an equation for a conservative force. It is that the force is equal to the negative of the derivative of the potential energy associated with that force with respect to position. For example, the force of a spring is equal to the negative of the derivative of the energy associated with the spring with respect to position. So it's equal to the negative of the derivative with respect to x of 1/2 kx squared. So please take the derivative of 1/2 kx squared with respect to position. Loki.
1K.
You're taking the derivative of 1/2 kx squared with respect to position.
1KX.
Right. So the force of the spring equals negative kx. Right? You've seen that before. We have the force of gravity equals the negative of the derivative of gravitational potential energy with respect to, in this particular case, because it's in the y direction, the derivative with respect to y. So that's the negative of the derivative of mgh. M is a scalar. G is a scalar. Neither of those depend on y. H is the position in the y direction. So what is the derivative of mgh with respect to y? Is that mg. So it works out to be negative mg because the force of gravity is down. So that's what this means. Let's do an example. Let's say we have a conservative force, and the equation for this conservative force is negative 4.0x plus 8.0x cubed in the I direction, n in newtons. And the question is, find the change in potential energy due to position from 2.0 to 4.0 meters. In other words, what is the change of potential energy associated with this when moving from 2 to 4 meters? Go ahead, Dorfstetter, ask me a question.
I just can't read it.
Dorfstetter, do you have your glasses? Why?
I forgot them.
It's sad. We have plenty of spaces up front, yet you should ask for things. Like Tyler's very nice. He can probably read from back there. Tyler, can you read from back there? All you'd have to do would be to ask.
No, I don't, but I feel bad.
You feel bad because you just keep asking Jerry what it says in the corner. I would stop feeling bad for that and start feeling bad for asking Tyler to switch with you. Tyler, thanks. So we're finding the change in the position, or sorry, change in energy, potential energy as a function of position from 2 to 4 meters. Thoughts? I need an approach, please. Andrew.
Can we like change around f of x is equal to the derivative of u with respect to x?
Uh-huh.
So then we can multiply both sides by the bottom of like d of x. And that's like the integral of f of x with respect to d of x equals the integral of nothing with respect to negative 2.
Okay. So let's rearrange this. If we take the integral here, this is going to be from u initial to u final. This is going to be position initial to position final. This right here is going to be the change in potential energy, delta u. That's going to be equal to the negative of the integral from position initial to position final of the force with respect to position. Hold on. The integral from initial to final position of the force with respect to position. That sounds familiar, Sierra. What is that?
It's the equation for non-constant work on a non-constant work.
So this is equal to the negative of the work done by this force. In other words, work is a transfer of energy. When you do work, you change the potential energy stored whenever you're doing work. That's what that means. So coming back to the particular problem, we have the change in potential energy is equal to the negative of, from position initial, which is 2, to position final, which is 4, of our force, which is negative 4x plus 8x cubed with respect to x. Please take the integral of negative 4x plus 8x cubed. Dorstetter?
Negative 4x squared divided by 2 plus 8x to the 4th. Oh, little bracket. 2, 4.
Don't forget your limits, and there was a negative out front there we don't want to forget about. So this is equal to, let me just carry through the negative so we don't forget about it. 4x, actually we'll drop some of the stuff here. So we have 2x squared minus 2x to the 4th power from 2 to 4. So what we end up with here is this guy, we have 2 times 4 squared minus 2 times 4 to the 4th power minus the quantity of 2 times 2 squared minus 2 times 2 to the 4th power. Good luck.
Which part? When you simplify the integral, did you switch to the negative? Or like, well, the negative?
The negative was here, the negative's on the outside, so the negative stayed on the outside, and I multiplied through by that negative here. Yeah, it was just to try to make it a little bit less complicated with all the negatives.
I think it's negative 456.
Negative 456 joules. Independent confirmation, negative 456 joules?
Yeah.
Yes. In other words, this particular force is actually taking energy away from the system. It might be decreasing the velocity, therefore decreasing the kinetic energy of the system. Who knows? I mean, we haven't set up specifics here. It's just a kind of a nebulous question. But
I know in your classes it's probably going to apply, but like on the AP test, do they want us to show our work for like doing definite integral?
for doing a definite integral, in other words,
Do
like
they want us to
this.
see all this? Yeah.
Yes, this would be the minimum of what I would suggest that you show, for me and for those who are not me. Curl your lip all you want. You still need to show your work.